Metals are key construction materials in today's world, which still being utilized in practically every bridge, building, and vehicle constructed. The preservation of those materials from corrosion is considered significant, both to ensure safety and to mitigate corrosion-related costs. Did you know that the percentage of corrosion-related costs could be avoided with the correct prevention and treatment solution? That's why corrosion protection of metal has become a critical issue to ensure the safety of structures, vehicles, and also a large extent for economic reasons. My name is Nurathilah. Here are my final year project studies that I would like to share with you today. Improving the lifetime of steel in the environment has become a key issue due to its broad application. Surface coating techniques have piqued the curiosity of both industry and scientific research. Based on Engine's term, coating is the most widely used technique since it can provide protection against general environmental conditions and greatly improve the lifetime of structures through reduced maintenance effort. In 2013, corrosion costs in the United States were estimated to be around 2.7% of gross domestic product, GDP. And now, corrosion costs in all industrialized countries range from 1% to 5% of GDP, which are very concerning. Superhydrophobicity is a widespread natural phenomenon that has been extensively investigated and researched. For application in a variety of fields for decades, especially as waterproof medium. The general technique for achieving superhydrophobicity is to develop micro or nanostructure out of low surface tension materials. In actuality, the majority of coating method documented to date rely on either reproducing pre-existing rough structures or producing roughness on existing material through multiple-step technique. Based on L.Zhang 2021, because of the scarcity of excellent natural templates and straightforward production technique, a coating process that is easy, low-cost, scalable, and environmentally friendly is high in demand. Until recently, corrosion protection could be efficiently performed using a superhydrophobic coating, but most studies either use complicated method or expensive composition. Therefore, these studies herein explore an unconventional fabrication technique for smart superhydrophobic coating via zinc oxide nanoparticles with a simple and inexpensive method. To achieve superhydrophobicity, physiochemical properties of the coating is studied in terms of wetting, morphology, and structural bonding properties. Furthermore, corrosion performance of the coating is investigated through salt spray condition, through visual inspection and study of wetting properties. The research scope of the study comprises the following part. First, fabricate superhydrophobic coating consisting of zinc oxide nanoparticles, epoxy, and stearic acid through solution casting method. The composition of the coating is based on 4:1 of zinc oxide to epoxy weight ratio, and the stearic acid concentration is 2.5% weight based on solvent used. The wetting properties of the coating is studied based on static water contact angle analysis. The morphological and the structural properties of the coating are covered with FISM, ETS, and FTIR respectively. The corrosion performance of the coating is studied in accelerated condition under salt spray testing according to ASTM B117 standard over a duration of 1 to 20 days. And lastly, the corrosion rate of the coating is monitored based on visual observation and changes in contact angle result after subjected to salt spray. So now you may ask, why did I choose to carry out this project and what the gaps of this research? L.Izzreen 2015 did fabricate a polydimethyl siloxane formulation containing hydrophobic silica nanoparticles with different addition of PDMS percentage, but the coating was not stable over a long time. With the presence of too much amount of PDMS, affect the contact angle and superhydrophobicity of the coating. Corrosion resistance of this coating only managed to survive less than 10 days, then the coating will crack under corrosive immersion, 3% and ACL water solution. This paper also performed a complicated method to achieve superhydrophobic coating. And few other papers display that treated or improvised composition are being used. It shows that the method and material itself already consuming a lot of pennies, which conflicted with the fact given by L.Zhang mentioned that straightforward production technique, process that is easy, low cost, scalable, and environmentally friendly is high in demand. In addition, a review by Zhang et al. 2016 reported that fabrication method mostly are laboratory scale and not yet ready for production of large superhydrophobic surface that could be potentially interesting for many real applications. This can be attributed to the complexity of hierarchical, micro, or nanostructure, as well as the costly low surface energy material. Further work are still required with focus on enhancing stability of superhydrophobic structure. Therefore, self-cleaning functionalities and corrosion inhibitor may be introduced for the design of smart superhydrophobic surface that can repair their anti-corrosive performance autonomously. The research methodology are: firstly, carbon steel grade S50C medium is cut into 2 by 2 cm in size. The substrate then undergoes surface grinding, then cleaned with generous amount of ethanol solution, rinsed with deionized water, and then dried under room temperature. Next, fabrication of superhydrophobic coating. Zinc oxide nanoparticles and stearic acid were dispersed into absolute ethanol solution with constant agitation. Then, the mixture solution undergoes ultrasonication using an ultrasonicator probe. Afterward, epoxy resin and hardener were added into the suspension and mechanically stirred. The result coating was piped onto the substrate and dried in room temperature. As for the characteristic, the surface morphology of the coating samples were assessed by FISM, FTIR, and EDS analysis, water contact angle measurement, surface waterability, which are water droplet adhesion and water repellency tests, self-cleaning test, salt test, and visual inspection for corrosion performance evaluation, and lastly, monitoring the changes of contact angle with interval of 20 days. The surface morphology of the coating samples was assessed by FISM image with different magnification. A shows the blank carbon steel surface with a water contact angle of 76.09 degree. B, EP coating surface with smooth surface which demonstrate a hydrophilic waterability with a water contact angle of 104.14 degree. And C shows the superhydrophobic zinc oxide nanocoating with contact angle of 166.60 degree. A comparison can be made here. EP coating is hydrophilic, proven that its lack of low surface energy, whereas to achieve superhydrophobicity, coating surface must demonstrate a low surface energy with the presence of surface roughness. So, the improvement in hydrophobicity of the zinc oxide surface over EP film is attributed to the aggregation of zinc oxide nanoparticles. And D shows the sliding angles below 10 degree which indicate superhydrophobicity property. Next are the 3D profiles of the coated samples, captured by LSCM to assess the average surface roughness result of EP and zinc oxide nanosuperhydrophobic coating. RA of the EP resin surface is 2.46 micrometer, which most likely due to the coarse structure produced on its surface. RA of zinc oxide nanosuperhydrophobic surface has increased to 3.77 micrometer. The increment average roughness was because of addition of stearic acid to the coating, which owing to the creation of richer topography induced by stearic acid modification. EDS and FTIR analysis were used to further the investigation. FTIR and EDS analysis can confirm the existence of stearic acid absorbed on the zinc oxide nano-coated surface. Result of water adhesion test shows that the water droplet that contact with superhydrophobic surface were detached from the surface without any residual. This due to the form of the air pockets layer in the interface of hydrochells of this superhydrophobic coating, and its low surface energy has resulted in its water impermeability. No water residual formed on the surface after the deformation process and detachment took place, proof that this zinc oxide nano-superhydrophobic film has a low water adhesion. This figure shows water repellency performance of blank metal and EP coating. However, on the zinc oxide nanosuperhydrophobic coating, water droplets bounce and roll off the surface without becoming wet. Based on the wetting characteristic and water repellency of the performance, the zinc oxide nanosuperhydrophobic coated surface demonstrates a high rapid sliding effect and repellency against water droplet, indicating its self-cleaning behavior. So next are the results of self-cleaning test. The contaminant contained within water remains on the surface of EP resin, as shown in B, while a similar tendency was observed on the zinc oxide nanosuperhydrophobic coating. The contaminant rolled off and carried away with the water droplet dripping down the coating surface. This clarifies that the rough surface of the zinc oxide nanosuperhydrophobic structure and its low surface energy have resulted in lower water adhesion to its surface. Hence, the adhesion between the contaminant and water droplet is stronger than the adhesion between the superhydrophobic surface and the contaminant, as mentioned in Liu et al. 2019. The experiment validates that the fabricate superhydrophobic coatings, self-cleaning property, and water repellency. For corrosion performance, all the samples undergo a salt spray testing with ASTM B117 testing standard to mimic corrosive study for 20 days exposure time. Samples were checked at 0, 3, 10, and 20 days. The image were recorded and as well as water contact angle. As you can see at the figure table, after 10 days, excessive amount of corrosion product can be seen on the uncoated sample surface. However, the amount of corrosion on top of zinc oxide nano-coated surface were very severe compared to EP resin surface. After 20 days, uncoated sample shows extravagant amount of corrosion product built up compared to EP resin and zinc oxide nano-superhydrophobic coated surface. However, EP resin exhibit minimum amount of corrosion, but a few blister and peeling while zinc oxide nano superhydrophobic coated surface samples remain intact with absence of little rust on scratch mark, no peeling, no blister, and completely clean surface after exposure. Based on the water contact angle reading trend, also result that the zinc oxide nano superhydrophobic coating maintain its superhydrophobicity even after exposed to harsh environment, which 166.60 degree before and 165.28 degree after the testing. To wrap up everything, this study had successfully fabricated a smart superhydrophobic coating via zinc oxide nanoparticles with simple strategy that focus on one-step solution coating deposition procedure. The smart superhydrophobic coating exhibit excellent water adhesion, water repellency, and self-cleaning property with water contact angle of 166.60 degree and sliding angle of 5 degree respectively. Based on visual inspection result, the coated surface samples remain intact with absence of little rust on scratch mark, no peeling, no blister, and completely clean surface after exposure, and also maintaining its superhydrophobicity. This shows that zinc oxide nano superhydrophobic coating function effectively as a corrosion protection and also perform a self-cleaning coating surface successfully. I believe that superhydrophobic surface created by a simple, cost-effective, scalable, and easy approach is a good candidate for usage as self-cleaning coating in a wide variety of applications due to its significant corrosion resistance and untreated and composition involvement. Thank you.